Well, a concept so mind-bending, it really makes you question what you think you know about empty space. Imagine for a moment that the very fabric of reality, the smooth, continuous space and time we experience, isn't smooth at all when you zoom way, way in.
That's exactly right. It's a powerful theoretical prediction.
Yeah.
At its most fundamental level, space-time is actually, well, turbulent. It's an ever-changing froth. We call it quantum foam.
And here's where it gets really interesting, because this deep dive is all about tackling maybe the biggest conceptual chasm in physics. On one side, you have Albert Einstein's general theory of relativity, beautifully describes the universe on grand scales, gravity as space-time's curvature. A smooth, continuous, dynamic picture.
And on the other side, quantum mechanics, governing the microscopic world.
Yeah.
Fundamentally discrete, probabilistic, where things come in these tiny quantized packets.
Right. So our mission for this deep dive is to explore how applying those quantum principles to gravity itself leads to this bizarre idea of quantum foam, what it might mean for reality, and crucially, how physicists are actually trying to, find it.
It's a huge puzzle.
So if we have these two incredibly successful theories, GR and QM, that work perfectly in their own domains, what exactly happens at the point where they meet? Or where they conflict? Where do things start to sort of break down?
Well, you have to go down to an unimaginably small scale. It's called the Planck scale. Think around 1035 meters for length and maybe 1044 seconds for time, just incredibly tiny.
Okay.
And down there, the predictions of both general relativity and quantum mechanics, at least in their current forms, they just don't play nicely together. They essentially give contradictory answers. It's like they're speaking different languages.
They need something new.
Exactly. To understand what's happening at that scale, we absolutely need a successful quantum theory of gravity. That's the holy grail, really.
And what's the fundamental engine driving this idea of space-time becoming foamy? Our sources point back to something core from quantum mechanics, Heisenberg's uncertainty principle. We often hear about it in terms of position and momentum, but there's another pairing that's critical here, isn't there?
There is, yes, and it's absolutely key. It's the less discussed but equally profound version relating uncertainty in energy delta E and uncertainty in time delta T.
Okay, energy and time, how does that work?
Well, think of it like this. Over extremely short intervals of time, the delta T, the uncertainty in energy, delta E, can become enormous.
Yeah.
Arbitrarily large, in fact. It means energy conservation can be sort of borrowed against for these incredibly fleeting moments.
Like the universe taking out a tiny, super short-term energy loan.
That's a great way to put it, yeah. Creating particles and antiparticles out of seemingly nowhere. But there's a catch. The bigger the energy loan, the faster it has to be paid back. These temporary energy spikes are what we call quantum fluctuations.
Okay, so these massive fleeting energy fluctuations are happening. And we know from general relativity that any form of energy actually curves space-time. Does that mean space-time itself, at these tiny scales and for these tiny moments, would be anything but smooth? Would it become jittery?
That's exactly it. You've got it. If you have these immense, albeit temporary, energy fluctuations popping up everywhere at tiny scales, GR tells us they must cause violent fluctuations in space-time geometry itself.
Right.
So instead of that smooth, gently curving picture, space-time at this fundamental level will be a chaotic, jittery, constantly changing landscape. That is the foam.
And what's fascinating here is how our modern understanding of the vacuum plays into this whole picture. Quantum field theory, QFT, it tells us that what we used to think of as empty space is, well, not empty at all.
Not even close.
Yeah.
It's permeated by fundamental fields, electron fields, photon fields, quark fields, the underlying reality of everything we see. And even in a perfect vacuum, the lowest energy state possible, these fields are never perfectly still.
They're always fluctuating.
Always. Ceaseless quantum fluctuations.
Yeah.
People sometimes visualize it as this seething and bubbling cauldron where virtual particles and their antiparticles are constantly, spontaneously emerging from the field and then annihilating each other almost instantly.
So these virtual particles, they aren't really particles like electrons or photons flying around, more like ripples in the field.
Exactly. They're more of a mathematical tool, a useful way to visualize and calculate the effects of these underlying field fluctuations. The key takeaway is that the vacuum isn't just empty nothingness. It has properties. It has energy.
Right, the vacuum energy or zero-point energy.
Precisely. And this isn't just theory. It possesses a measurable, non-zero energy that has very real, observable consequences. Things like the Casimir effect, the Lamb shift. We can actually measure this stuff.
Which we'll definitely get into.
Yeah. So quantum foam is really the logical extension of all this. What happens when these vacuum fluctuations become so energetic, so extreme at the Planck scale, that their gravitational effects, according to GR, start to seriously curve and distort spacetime itself. That's when the void transforms into this dynamic, fluctuating foam.
Okay, so if the vacuum is this seething cauldron of energy, who was the first person bold enough to really connect those dots and imagine what it meant for spacetime itself?
That would be the brilliant physicist John Archibald Wheeler, a true giant. Back in 1955, he coined that wonderfully evocative term, quantum foam, or sometimes spacetime foam.
Wheeler. Okay.
His genius was in synthesizing the implications of both general relativity and quantum mechanics. He argued very persuasively that, look, if spacetime is truly physical, if it's dynamic like GR says, then it must be subject to quantum mechanics rules too. The probabilistic nature, the fluctuations, it can't be exempt.
So he basically said spacetime itself has to fluctuate.
Yes, he proposed that the very geometry of spacetime fluctuates. It was a radical idea back then.
So quantum foam isn't just some wild speculative theory cooked up out of nowhere. It sounds less like a specific theory and more like a prediction, something that any good theory of quantum gravity has to deal with.
That's a perfect way to frame it. It's less a theory itself and more a phenomenon or prediction that any successful unification of GR and QM must account for. Our source calls it an inescapable logical consequence of pushing our two best theories to their combined limit.
So the debate isn't really whether spacetime has quantum properties down there, but more about what those properties actually look like.
Exactly. What is the nature of that foam? Is it discrete? Does it violate symmetries? That's where the different theories come in.
Now, when we talk about something this mind-bending, this quantum foam, it's really easy to get confused about scale. Is this foam happening inside atoms? I imagine that's a common first thought. But we need to be crystal clear about the scales involved here, right? It's not in the atom.
Absolutely not. This is a crucial point and a common misconception. The scales are just vastly, vastly different. Quantum foam is not some substance contained within an atom. Think of it more like LO is at. The atom is this enormous structure that exists within and floats upon this incredibly fine-grained, fluctuating spacetime. The foam is the texture of the sea. The atom is a giant ship on it.
Let's try to put some numbers on that. An atom, typically around 10 meters across.
Roughly, yeah. And the nucleus at its heart. That's way smaller, down around 10, 15 meters.
So the nucleus is like 100,000 times smaller than the atom itself. Our source had a great analogy. If the nucleus was a blueberry,
the entire atom would be the size of a football stadium. Mostly empty space, just assigned by where the electrons might be, those probability clouds.
Okay, so that's the atomic scale. Now, where does the Planck length fit in? The scale where quantum gravity supposedly takes over.
We have to go much, much, much smaller. The Planck length is about 1.6 times 10^35 meters. It's derived from fundamental constants, the speed of light, Planck's constant, Newton's gravitational constant. It represents the scale where the quantum effects of gravity are expected to become dominant, where space-time itself gets quantized somehow.
And it's important to stress, it's not just like the universe's smallest possible pixel, right?
Right.
There's a deeper reason we think it's a limit.
Right. It's not quite that simple. The thought experiment goes like this. To probe something that small, to measure it, you'd need incredibly high energy, Planck energy levels. But if you concentrate that much energy into such a tiny region, you'd inevitably create a microscopic black hole. It would swallow the region you're trying to measure and your probe along with it.
So the very act of measuring destroys what you're trying to see. That really highlights why we need new physics, new ideas beyond just GR and QM as they are.
Precisely. It shows the breakdown point. Now, let's compare those scales again. A proton is already tiny, but it's about 10 and 20 times. That's 100 billion times larger than the Planck length.
Wow.
A hydrogen atom is about 125 times larger. The scale of the foam itself, the bubbles or fluctuations, are predicted to be, get this, about 10 times a billionth of the diameter of a hydrogen atom's nucleus.
Okay, my brain hurts trying to visualize that. It's just staggeringly different scales.
It really is.
So here's maybe the most profound insight from all this scale talk, something our sources really emphasize. The very fact that atoms exist, that they're stable, that chemistry works, that tells us something incredible about this quantum foam.
It does. It implies that all that unbelievable chaos predicted at the Planck scale must somehow average out almost perfectly by the time you get up to the scale of atoms and molecules. The smooth, predictable space-time of general relativity that we experience and that atoms rely on has to emerge from this underlying frenzy.
So if the foam didn't average out so well, what would happen?
Well, think about atoms. They're held together by electromagnetic forces, Electrons exist in stable, quantized energy levels. If the very space-time points those electrons occupy were violently fluctuating, randomly changing the local electromagnetic potential, those stable energy levels would be completely disrupted. Chemistry as we know it wouldn't exist. Stable matter couldn't form.
So the writhing barrel of eels down at the Planck scale somehow looks like a smooth barrel of concrete from the atom's perspective.
That's a fantastic analogy, yes. The very existence of our relatively stable, low-energy universe implies this incredible averaging out must occur. There's a hidden order that tames the foam.
Okay, so while directly seeing the foam's effect on an atom in the lab seems impossible due to the scale, are there more subtle influences? Maybe indirect evidence or hypothetical effects physicists are looking for?
Yes, absolutely. There are phenomena that, while not direct proof of space-time foam, strongly support the underlying principle, namely the reality of vacuum fluctuations. These provide the empirical motivation. And then there are the more speculative, hypothetical direct effects that people are actively hunting for, effects that would arise if space-time itself is quantized.
So let's start with that indirect evidence, the stuff that builds the case. Things like the Casimir effect and the Lamb shift. How do they fit in?
Right. These are crucial because they're not direct observations of fluctuating space-time, but they absolutely confirm the reality of vacuum fluctuations, particularly in the electromagnetic field. And those fluctuations are the bedrock of the quantum foam hypothesis.
Okay, explain the Casimir effect first.
Sure. Imagine you take two perfectly reflective, uncharged metal plates and place them incredibly close together in a perfect vacuum, like nanometers apart. What you find is a tiny attractive force pulling them together.
Why? There's no charge, no gravity.
It comes from the vacuum fluctuations. The space between the plates restricts which wavelengths of virtual photons can exist there, only those that fit perfectly. But outside the plates, there's no such restriction, so you have more virtual photons pushing inward from the outside than pushing outward from between the plates. This imbalance creates a net pressure, pushing the plates together.
Wow. So it's a measurable force generated purely by the vacuum's energy.
Exactly. It's a macroscopic consequence of vacuum energy. It's been measured very precisely.
Okay, and the Lamb shift. That's about hydrogen atoms, right?
Yes. Theory initially predicted two specific energy levels in the hydrogen atom should be exactly the same. But experiments showed a tiny difference. Quantum electrodynamics, or QED, explains this shift by saying the electron isn't just orbiting the proton. Its position is constantly being jiggled or perturbed by its interaction with the surrounding vacuum fluctuations, those virtual photons.
So the vacuum is literally nudging the electron slightly.
In a way, yes. This interaction slightly shifts its energy levels. The electron's anomalous magnetic moment, how it behaves like a tiny magnet, is another example where calculations including these vacuum interactions match experiments to incredible precision.
So these effects, Casimir and Lamb, they're foundational. They prove the vacuum isn't empty, it's a dynamic medium full of field fluctuation.
Precisely. And the logic then goes, okay, we know these vacuum energy fluctuations are real.
Yeah.
General relativity tells us energy gravitates, it curves space-time. So what happens when these fluctuations get really intense at the Planck scale? They must have gravitational consequences. Quantum foam is the name we give to those predicted gravitational consequences.
Got it. That builds a strong case. Now, what about those more speculative, direct effects? If space-time itself is a quantum system, how might that show up?
Well, it gets even more subtle. If space-time itself is fluctuating, it might add another layer of jitter to particles, beyond the jitter from virtual particles. So an electron moving through this foamy space-time might experience tiny random kicks, not just from the electromagnetic vacuum, but from the geometry itself.
Could that affect atomic energy levels?
Some speculative models propose just that, minute corrections to atomic spectra, maybe tiny modifications to how atoms respond to magnetic fields, like the Zeeman effect. There are ideas linked to a generalized uncertainty principle that might arise from quantum gravity.
And what about this idea of space-time-induced decoherence? That sounds really deep.
It is potentially profound. Decoherence is the process by which quantum systems lose their quantumness, their ability to be in superpositions, for example, through interaction with their environment. It's key to explaining why we see a classical world emerge from a quantum substrate.
Usually the environment is like air molecules or photons.
Right. But what if quantum foam provides a fundamental, inescapable, universal environment? What if the constant jittering of space-time itself forces quantum systems to decohere, even in a perfect vacuum, totally isolated from everything else?
So the foam itself could be the reason the quantum world transitions to the classical world we see.
That's the speculation. It would be an intrinsic decoherence mechanism. For an atom, it might mean its energy levels aren't perfectly sharp, or that quantum superpositions naturally decay over time, even with perfect shielding.
How on earth would you test that?
It would be incredibly difficult, because the effect is predicted to be extraordinarily weak. But physicists are looking at systems that maintain quantum coherence for a very long time. Maybe neutrino oscillations, where neutrinos travel vast cosmic distances changing type. Or perhaps the qubits in future highly sensitive quantum computers might eventually be limited by this fundamental decoherence. It's a cutting-edge search.
Okay, so if lab tests are mostly looking for these incredibly subtle effects, how do we get a more direct handle on the foam itself? Given the Planck scale is just so far beyond our reach experimentally, our sources say the strategy is kind of counterintuitive. Use the entire cosmos as your laboratory.
That's the main approach right now, yes.
Yeah.
If you can't build a microscope powerful enough to see the Planck scale, maybe you can see the accumulated effects of that scale over vast distances. Look for tiny imprints left on particles that have traveled across billions of light years.
Cosmic messengers, like photons from really distant, bright objects.
Exactly. High-energy photons from things like gamma-ray bursts, GRBs, these incredibly powerful explosions across the universe, or active galactic nuclei, AGNs, like quasars and blazars, which are supermassive black holes feeding in the centers of distant galaxies. They're ideal because the photons travel for billions of years, giving any tiny effect plenty of time to build up, and their high energy makes them potentially more sensitive to space-time structure.
So what kind of effect are they looking for?
One main test is the time-of-flight measurement. It's looking for something called Lorentz invariance violation. See, Einstein's theory says the speed of light in a vacuum is constant for all observers and all energies. But some models of quantum foam predict that space-time might act like a kind of refractive medium.
Meaning light of different energies might travel at slightly different speeds?
Potentially, yeah. The idea is that higher energy photons with their shorter wavelengths might feel the graininess or foaminess of space-time more acutely than lower energy photons. If that's true, they might travel just a tiny bit slower.
So if you look at a GRB, which releases photons across a huge energy range all at once,
You'd expect the highest energy photons to arise slightly later than the lower energy ones if they've traveled billions of light years through this foamy medium, and the delay should be proportional to the distance traveled.
and there was that one result, GRB 080916C, sounded promising.
It did. NASA's Fermi telescope observed this burst from 12.2 billion light-years away. If highest energy photons arrived about 16.5 seconds after the lower energy ones, that caused a huge stir.
But
Subsequent analyses of many other GRBs haven't found a consistent pattern. Sometimes there's a delay, sometimes none. Sometimes the high-energy photons even arrive first. There's no clear correlation with distance. So the current thinking is that these observed time lags are probably due to complex physics happening at the source of the GRB, not an effect accumulated during propagation through space-time.
okay, so time of flight isn't giving us a clear signal. What about the other big test, the image blurring idea?
Right. The logic here is similar to how Earth's atmosphere makes stars twinkle and blurs images from ground-based telescopes. If space-time itself is foamy and fluctuating, it should subtly distort the wavefronts of light passing through it. Over billions of light years, this could accumulate, causing images of very distant, point-like objects like quasars to appear slightly blurred.
And higher energy light, like X-rays or gamma rays, should be blurred more.
That's the prediction of many simple models, yes. Shorter wavelengths should interact more strongly with the small-scale foam structure.
So what have X-ray and gamma ray telescopes seen?
Here, the results are even more striking and frankly constraining. Observatories like NASA's Chandra X-ray Observatory, Fermi again for gamma rays, and ground-based arrays like Veritas. They've observed distant quasars and found remarkably sharp images, even in X-rays and gamma rays.
No blurring.
Essentially none detectable, down to very impressive limits. This lack of blurring has actually ruled out several of the simpler models of quantum foam, like ones called the random walk model or the holographic model mentioned in our sources.
So the verdict from the cosmos seems pretty profound, no definitive detection yet, but these null results are really powerful, aren't they?
They absolutely are. They don't mean quantum foam doesn't exist, but they tell us that if it does, its structure must be much more subtle. The fluctuations can't just randomly accumulate in the way these simple models assumed. The universe, observationally, appears incredibly smooth and respects Lorentz invariance to an extraordinary degree, even over vast distances. This forces theorists back to the drawing board to develop more sophisticated ideas.
Which brings us neatly to those more sophisticated ideas, the actual competing theories of quantum gravity. Because as you said, quantum foam isn't a theory itself, it's more the thing these theories need to explain or incorporate.
Exactly. It's the predicted battleground, and different theories describe that battleground very differently.
Okay, so leading the pack, or at least one major contender, is loop quantum gravity, LQG. This sounds like it takes Wheeler's foamy idea quite literally.
It absolutely does. LQG is what we call a background-independent theory. It doesn't start with a smooth spacetime and then quantize stuff on it. It quantizes spacetime itself. In LQG, space at the Planck scale isn't continuous. It's fundamentally discrete, woven from abstract structures called spin networks. Think of nodes representing quanta of volume and links representing quanta of area.
So space comes in minimum chunks.
Essentially, yes.
Yeah.
And the history of how these quantum geometries evolve and change is called a spin foam. So in LQG, the spin foam is the quantum spacetime. It directly realizes Wheeler's fluctuating geometry. The Planck length emerges as a genuine minimum distance.
Okay, that's one vision. Then on the completely other side of the theoretical spectrum, you have string theory. Radically different approach, right?
Radically different, yes. String theory doesn't try to directly quantize GR or spacetime in the same way. Instead, it changes the fundamental constituents of reality. It says elementary entities aren't zero-dimensional point particles, but tiny one-dimensional vibrating strings.
And different vibrations are different particles.
Exactly. Different vibration modes correspond to different particles, electrons, quarks, photons, and crucially, the graviton, the carrier of the gravitational force. Because strings are extended objects, not points, their interactions are sort of smeared out. This naturally tames the infinities that plague attempts to quantize gravity with point particles. The very infinities that lead to the problematic divergences suggesting a wildly fluctuating foam.
So string theory kind of smooths out the problem before it starts.
In a sense, yes. It resolves the issue by changing the fundamental nature of particles and interactions at high energies. The foam problem gets addressed differently.
And string theory famously requires extra spatial dimensions, right? Like 10 or 11 total.
That's right. That's a core prediction. In string theory, the foam concept is replaced by the complex dynamics of these strings and higher dimensional objects called branes moving through this expanded multidimensional space. And some modern versions, like at SCFT, even suggest our familiar 4D spacetime might be an emergent holographic projection from physics happening on a lower dimensional boundary. Very different picture.
Wow. Okay, so LQG and string theory are the big two. But there are other ideas out there, too, a whole landscape.
Oh, yes. It's a vibrant field. You have things like causal set theory, which proposes that the fundamental structure is just a discrete set of space-time atoms linked only by cause and effect relationships. Smooth space-time emerges statistically from this network.
Interesting.
Then there's asymptotic safety, which explores the possibility that quantum gravity might actually be consistent without needing fundamentally new ingredients like strings or loops. It suggests the theory's parameters might behave nicely at high energies, taming the divergences naturally.
And emergent gravity. That sounds intriguing. Gravity isn't fundamental.
That's the idea in some models. Maybe gravity and spacetime aren't basic building blocks, but rather emerge from more fundamental, underlying microscopic degrees of freedom, possibly related to thermodynamics or quantum entanglement, like how fluidity emerges from discrete molecules.
So many different ways to approach the problem.
Absolutely. Twistor theory, non-commutative geometry, lots of different conceptual frameworks trying to reconcile gravity and the quantum world, each with different implications for what happens at the Planck scale, for what replaces that simple idea of foam.
This quest for quantum foam and the broader search for quantum gravity, it really feels like it's not just about understanding the incredibly small. It seems to connect to some of the biggest, most persistent mysteries in cosmology and fundamental physics.
It absolutely does. What's so compelling and maybe daunting is how several major unsolved problems like the nature of dark energy, the stability of our universe, the information paradox of black holes, all seem to converge on this single foundational issue: understanding the quantum structure of space-time and the vacuum.
Okay, let's tackle the big word first. The cosmological constant problem. You mentioned it earlier, often called the worst theoretical prediction in physics history. How does quantum foam feed into that?
It's truly staggering, yeah. As we discussed, quantum field theory predicts that the vacuum, with all its zero-point energy from fluctuating fields, should have an enormous energy density. According to general relativity, this energy density acts like a cosmological constant. It should make space-time curve catastrophically. The prediction is about 120 orders of magnitude. That's a 1 followed by 120 zeros, larger than the actual observed value of dark energy, which is driving the universe's gentle acceleration.
120 orders of magnitude off. That's not even wrong. It's spectacularly wrong.
Exactly. It's a monumental failure of our current understanding when combined. And quantum foam is right at the heart of it. The very same vacuum fluctuations that are predicted to give spacetime its foamy texture at the Planck scale are the ones contributing to this enormous theoretical vacuum energy.
So the foam is both the source of the problem and potentially part of the solution.
That's the hope. Perhaps a full theory of quantum gravity will show how these violent Planck scale fluctuations conspire to average out to almost exactly zero on large scales, canceling out that huge energy. Or maybe the foam structure itself is somehow related to the small residual dark energy we do observe, perhaps via hypothetical objects called genes, which are like particles made of pure geometry. It's a huge driver for quantum gravity research.
Okay, what about the stability of our vacuum? This idea that maybe our universe isn't truly stable, tied to the Higgs field.
Right. The Higgs field gives particles mass, and its value determines the energy state of our vacuum. Based on the measured masses of particles like the Higgs boson and the top quark, calculations suggest our universe might not be in the absolute lowest possible energy state. It might be in a metastable state, like a ball resting in a small dip on a hillside, rather than at the bottom of the valley.
Meaning it could tunnel through to the true lower energy vacuum state.
Potentially, yes. A quantum tunneling event could trigger a transition to this true vacuum. If that happened, the fundamental constants of nature could change drastically, and structures like atoms might become impossible. It would be catastrophic. Now, the likelihood and timescale for this depend crucially on physics at very high energy scales, precisely the regime where quantum gravity and foam effects dominate. Some speculate that microscopic black holes, potentially created and evaporating within the quantum foam, could act as seeds for this vacuum decay, potentially shortening the universe's expected lifespan.
So the nature of the foam could influence the ultimate fate of the universe.
It's a possibility that highlights how interconnected these fundamental questions are.
And we can't talk quantum gravity without touching on black holes, information, and the holographic principle. You mentioned this briefly, the idea that information in a volume is encoded on its surface area. How does that connect to foam?
It's one of the most profound and counterintuitive ideas to emerge from thinking about black holes and quantum gravity. Black hole thermodynamics suggests the maximum amount of information or entropy you can pack into a region of space isn't proportional to its volume, as you'd expect, but to its surface area, measured in units of the Planck area, no less.
Like all the 3D reality inside is somehow projected onto a 2D boundary.
That's the holographic analogy, yes. It suggests a deep connection between gravity and information, and hints that maybe spacetime itself is emergent. Where does quantum foam fit in? Well, if spacetime is fundamentally granular at the Planck scale, perhaps those foam bubbles or bits are the fundamental degrees of freedom, the carriers of this information. The holographic principle then becomes a fundamental rule governing how densely this information can be packed.
So it recasts quantum gravity almost as quantum information theory.
In many ways, yes. It leads to ideas like it from Quibbit, where spacetime geometry might emerge from the entanglement patterns of underlying quantum information bits. Entanglement becomes the thread stitching the geometry of spacetime together. The foam represents the pixelation of that geometric tapestry.
And finally, pulling back a bit, the philosophical implications here are just huge, aren't they? Quantum foam seems to challenge our deepest intuitions about reality.
Absolutely. Yeah. It forces us to confront the limitations of our classical worldview, the idea of a smooth, continuous, deterministic spacetime background. Quantum foam suggests that's just an approximation, an illusion that breaks down at the smallest scales.
So things like determinism versus indeterminacy.
If the very fabric of reality is fundamentally probabilistic and fluctuating, does that imply the universe is inherently indeterministic at its core? It certainly points that way.
Continuity versus discreteness.
If space-time is discrete, made of foam or granules, that might resolve ancient paradoxes, like Zeno's paradoxes of motion. But it raises new, deep questions about how motion even works, how symmetries like Lorentz invariants are preserved or modified.
And time itself, you mentioned it might not be fundamental.
That's a common feature in many quantum gravity approaches, especially background-independent ones like LQG or causal sets. Time, as we experience it, a continuous flow, might be an emergent property of underlying, perhaps a temporal quantum processes. What that even means for causality is a profound philosophical question.
And locality, the idea that things are only affected by their immediate surroundings.
That too might be emergent. If spacetime geometry arises from non-local quantum entanglement, as some holographic ideas suggest, then locality might not be a fundamental feature of reality. Our local world could just be an effective, large-scale description of a fundamentally non-local substrate.
Wow. The core takeaway seems to be our everyday intuitions about space, time, cause, and effect are just not equipped for the ultimate nature of reality.
They're incredibly useful for navigating our macroscopic world, but they seem to break down completely when we probe the foundations.
So this whole journey into quantum foam, it really is a trip to the absolute limits of what we know and maybe even what we can know.
It starts with that fundamental clash, that tension between general relativity's smooth curves and quantum mechanics' discrete jumps. That tension forces us to imagine something new at the Planck scale. Quantum foam emerges as the logical consequence, this picture of space-time not as a passive stage, but as a dynamic, turbulent, fluctuating medium at its deepest level.
Okay, so let's synthesize all this. We've seen there's really strong theoretical motivation for some kind of quantum structure to spacetime. It seems almost unavoidable when you combine GR and QM. And we have solid indirect evidence, like the Casimir effect and the Lamb shift, confirming that the vacuum is fluctuating, providing the engine for the foam.
Right. But then on the other hand, the direct observational searches looking for those accumulated effects on light from distant cosmic sources have, so far, come up empty for the simpler models. The time-of-flight tests show no consistent energy-dependent speed difference. The image blurring tests show remarkably sharp pictures. These null results are powerful. They tell us space-time is incredibly smooth, much smoother than naive foam models predicted.
So the nuanced conclusion seems to be the universe's fundamental substrate is very likely a dynamic, fluctuating quantum medium of some kind. That seems hard to avoid. But its structure must be far more subtle, far more sophisticated than just a simple churning froth. There must be some hidden order, some mechanism that makes all those Planck scale fluctuations average out with extraordinary precision, giving us the smooth, classical world we see.
Exactly. The quest now isn't just to find the foam, it's to uncover this deep, subtle structure. What is the organizing principle? How does smooth space-time emerge so perfectly? That's the challenge for theories like LQG, string theory, and the others.
And the way forward involves looking even harder, with even better tools.
It has to be a multi-pronged attack. Next-generation particle colliders, like the proposed future circular collider, could potentially discover new particles predicted by theories like string theory, or find tiny deviations from the standard model that hint at quantum gravity effects.
And gravitational waves seem like a huge opportunity here.
Absolutely crucial. Next-generation gravitational wave observatories, ground-based ones like the Einstein telescope or Cosmic Explorer, and especially the future space-based LISA mission, are incredibly exciting. They might be sensitive enough to detect a faint, persistent background hiss of gravitational waves originating from the quantum fluctuations of spacetime itself in the very early universe. A direct probe of primordial foam, potentially.
Wow, hearing the sound of space-time forming?
It's a tantalizing possibility. And alongside that, precision quantum experiments here on Earth are pushing boundaries, using ultra-precise atomic clocks or atom interferometers that use the wave nature of atoms. Scientists are searching for those minute effects we discussed, like gravitationally induced decoherence or tiny violations of fundamental symmetries. It's a complementary lab-based approach.
So, thinking about all this, the quest for quantum foam, it really transcends just physics, doesn't it? It feels like it digs into the very nature of reality itself. Maybe the atom isn't just floating in a foamy sea. Maybe the atom and the foam are just different ripples, different manifestations of some single, deeper underlying reality, perhaps informational, perhaps computational.
That's the kind of profound shift in perspective this research evokes. Ideas like spacetime emerging from quantum entanglement suggest that the very glue holding the universe together might be quantum information. This deep dive into quantum foam really shows us how our biggest questions about space, time, matter, gravity, information are all converging. We're pushing the absolute boundaries of understanding the cosmos and, ultimately, our place within it.